So you can all see my
online.
PowerPoint.
All right. We should start right now, Sergio, or
1 minute to be Britannic, as we used to say here. British. Go ahead, Javan.
So this SSBD was supposed to be in which city? In Brazil, or was it always going to be virtual?
Okay.
No, it was in Búzios, in Rio.
Oh, in Rio. Oh.
All right.
Okay.
Nice.
Patrick and I were remembering 1986. Yeah, no, 89, 90.
No,
when it
1990.
Was in 1990, yeah, in Copacabana Palace, yes.
I was organizing.
It was really nice.
As a student.
Yeah, 1990, exactly.
Okay, so let's start then. All right, so I want to, already thank Emery again for giving us, this tutorial. It's the third tutorial in the SBBD of this year. And Emery is going to, present the tutorial with some of his collaborators, and he's going to present them later on. But I just wanted to say some words about Emery. It's Emery El-Habad, and he's a professor of computer science at the University of California, Santa Barbara. He received his bachelor engineering from Alexandria University, Egypt, and his PhD from Cornell University. His research interests are in the field of fault-tolerant distributed systems and databases, focusing recently on cloud data management and blockchain-based systems. Professor El-Habad is an ACM Fellow, AAS Fellow, and an IEEE Fellow. He was a chair of the Computer Science Department at UCSB, California, Santa Barbara, from 2007 to 2011. He has published over 300 articles in databases and distributed systems, and has supervised over 35 PhD students. Please, Emery, go on. Thanks.
Thank you very much. Thank you, Javar. Thank you for inviting me. It's always a pleasure to come to SBBD. As we were reminiscing, the first time I came was probably one of the first times I gave a keynote at a conference, and that was in 1990. And then I've been in Rio and in São Paulo, especially São Paulo. What we're going, it's a pity this time it's virtual, but this is the best that we can do under the circumstances. But I've been promised to come back to Brazil soon, so don't worry.
Thanks.
So this tutorial is an abbreviated version of a tutorial that we gave at VRDB, actually in Rio a couple of years ago, and then was modified and expanded last year in SIGMOD. And so we are going to kind of cover most parts of it. We'll see how the time goes. So this is obviously with my colleague Divi Agrawal, who's a professor at UC Santa Barbara, and we've been working together for as long as I've been in Santa Barbara. Divi was also chair of the computer science department and is also a AAAS fellow, an ACM fellow, and an IEEE fellow. This is also, we're going to have three of our students and ex-students. Mohammed Amiri, who graduated last summer, end of last spring. and he's now a postdoc at University of Pennsylvania. Victor Zachary, who graduated a year ago and is now at Oracle, and Sujaya Maya, who is still a PhD student and working with us. So this tutorial is going to cover basically blockchains. It's an introduction to blockchains, as well as highlighting two particularly important things: the importance and the foundations of databases and distributed systems on the development of blockchains, and the ideas from databases and distributed systems that permeated and have made blockchain a reality. Most of the time, we will be focusing on the type of blockchain that has become very popular with cryptocurrencies, so permissionless or public blockchains. However, we will also spend some time discussing a particular kind of blockchain, which is the private blockchain, where you know all the individuals, and that's called the permissioned blockchains, and that has gained a lot of interest in the database community in particular. I would be amiss to mention that an important and integral part of blockchains is tolerance to malicious, untrusted infrastructure. And so what is needed here is also a lot of cryptography. And we are not experts in cryptography. However, we use the tools from cryptography to show you how blockchain uses cryptography with distributed systems and database foundations to deliver what it is developing. So what I'll start with is an introduction of how Bitcoin, and in particular blockchain, was developed. So if we start, traditional banking, and this is where the notion of money comes in, starts by having banks that are institutions, which are, as you see in this picture, big, concrete, huge buildings that exude trust. We have these banks, and individuals like me and you and Marta would have accounts in these banks, and then we interact with each other. How do we interact with each other? This is what databases have been doing for a long time. Basically, I want to give Fabio some money, so what I do is I write a check, and the check is on money that I have in my bank account, and Fabio, sitting in Brazil, will take my check and give it to his bank. What happens as a result is that the banks interact with each other and result in the transfer of the money so that eventually it gets to him. So from a traditional point of view, we have, let's take as an example a check. So important things in a check are that you write the name of the recipient, so Fabio Porto, for example, and you write the amount of money that is going to be transferred, and critically, you sign it. I have to sign it. So we need a notion of identifying individuals, Fabio, Marta, Hacham, etc. And we need a way for me to be able to sign checks so that they are verified, and nobody should be able to forge my signature. And if I identify somebody, everybody would know who I'm talking about. What does the bank do? The bank keeps track of all the transactions that have been taking place. How does it do that? It keeps a ledger, basically a database or a log that keeps track of all that has been happening. Amr gave Muhammad some money, Muhammad gave Victor, so the money has transferred from one to the other. And this can go across different banks. The way people interact with each other is through transactions. So transactions transfer money from Alice to Bob, from Bob to Carol, etc. In databases, we would like to have good performance. So what do? We allow these transactions to be executed concurrently. So while I'm transferring money to Muhammad, Victor can transfer money to Marta, and so on. How do we make sure that the execution is correct? If there are conflicts, for example, I might be giving money to Muhammad and Muhammad then giving money to Victor. So now there is a conflict on Muhammad, on the data that Muhammad has, on the money that Muhammad has. So we need a way to manage this concurrency. And there is a long history since the old days when Jim Gray and others developed concurrency control, two-phase locking, all of these great techniques. We also need to make sure that even if failures happen, and the traditional database systems assume crash failures, so in that sense, we need to make sure that all the transactions are stored in this log, in this ledger, and this ledger is persistent. And the traditional way of ensuring persistency is by putting the log on disk. So disk is considered the reliable entity that survives failures. If you're not happy with that, you can go to tapes, etc. But for regular databases, this is a typical discussion. And since this disk with the log of all the information is being stored in the bank, in the infrastructure of the bank, we trust the bank. Remember, that was the picture I had before. So we trust the bank. We assume that the worst that can happen is crashes. So we trust that the information is going to be tamper-free. There's nothing bad that is going to happen. Okay, now comes Bitcoin. So what does Bitcoin do is it says, instead of having this big stone building that is the bank that we all trust, we're going to remove it and replace it with a peer-to-peer network. And that's the Bitcoin peer-to-peer network. Who are the peers? Everybody. Anybody in this room. How many participants are there in this room? Everybody can come in. If new people come in and I see the attendance risk keeps increasing, people can join this and they will get a copy of what we're dealing with, the ledger basically. If people are bored, you're welcome to leave. You can just leave. So the number of people in this big peer-to-peer network that is replacing the trust that we had in the bank is being distributed among all of you, among a lot of people scattered around the world. Not only that, I don't know everybody in this room. Okay, I know Fabio, I know Hakam, I know Marta, I know a few of you, but I don't know everybody. Do I trust everybody? Not necessarily. Hopefully, most of you will be trustworthy, but it is possible that some are not. So the infrastructure has to take care of this. It has to worry about these issues. So if we go back to the example of the checkbook, what we are doing is we need to have ways of identifying people. So we need, and the way they do it is they replace it using public and private keys. And I will explain this. The ledger is replaced with what's called a blockchain, which is basically a linked list. And instead of concurrency control, a notion of mining is going to be developed. And in Bitcoin, it's called proof of work. Instead of relying on the disk, which is persistent, we're going to have replication. We're going to have copies that are given to all the entities in this peer-to-peer network. So replication replaces the disk for persistence. And there are lots of interesting techniques that were developed to ensure that the log is immutable and tamper-free. So let me start by going through some of the basic foundations. So there is the public key and private key encryption, which is basically everybody can generate a public and a private key. They're generated in pairs. The public key is public, everybody knows it, and in a sense is my identity. Traditionally, public keys are used for encryption, but in blockchain, they are mainly used for identification. So I know Sujaya by her public key. That's how, and everybody would know her by that name. On the other hand, the signature, nobody knows. So you can think of the public key as something that I put on a billboard on top of my house, and I say, "This is, if you want to send me an email, you just address this." The signature, I'm the only one who knows it. And what's interesting is that they are used to verify the documents. So if there is a message, you can encrypt it using your private key, and you broadcast it, you send it to everybody. Anybody who has the public key can decrypt it and verify that it was actually sent by an Abedi. So It is unique for this particular signed document. It's a one-way function, so it's very hard to forge. You can know my public key, but you don't know my private key, and it's very hard to figure out my private key from the public key. However, if I publish something, it's very easy to verify it, that it was actually signed by me by knowing my public key. So it's a one-way function that can be very useful. So how does blockchain use this? And this idea goes back to David Chum from the 1990s. It's not new. A lot of the ideas that were used in Bitcoin came from all over the place in computer science, whether it's cryptography, digital currencies, cryptography, distributed systems, databases. What's interesting is Bitcoin brought all these together in an interesting way. One can criticize it, but it is still interesting and worth understanding. So I have some coins, and I'm Alice. I want to give some of my Bitcoins to Bob. So what do? I take my Bitcoin, which is basically a string, and I attach to it the public key of Bob. So now you have the Bitcoin, the amount, and attached to it the public key of Bob. So if somebody can read it, they can know that this is for Bob. And what do? Alice signs it using her private signature and puts it out. She's going to put it in the blockchain, but basically broadcast it. Once it's signed, anybody can actually verify that this was Alice who signed it, because everybody knows Alice's public key, and they can from it know that the money, they can decrypt it and figure out that the money was actually given to Bob. Now, so it can be verified and can go on. Now, Bob now has the money now that has Alice's signature, giving it to him. So what Bob can do is Bob can actually do the same thing, can take the money that he has and add Diana's public key, so passes it on to Diana, signs it, and puts it out, and so on. Now Diana can put Fabio's public key and sign it using her public signature, and so on. So we have a string, and it's interesting because what's happening now, we have an entire provenance of where the money came from and where it is going to. So that is one aspect of blockchains that is quite interesting. You know the entire history. It's not like the money that I have in my pocket. The money that I have in my pocket, if I give it to Muhammad, Muhammad cannot tell where I got this money from. So there's this history that is quite interesting, and provenance becomes important. Lots of interesting challenges. We are going to touch on a few of them. So in particular, how do I combine these different things? If I left like this, I would have a humongous string. I'd like it to be finite sized. So we're going to look into that. And what happens if, could I just copy the string? It's all in memory, and just give it to different people. So that's the big problem in cryptocurrencies called double spending. So the tool that we use is hashing, and you're all familiar with hashing, so I'm going to go quickly through it. Basically, you take any string of any length and you're going to hash it into a domain that is fixed. And the output size in Bitcoin is fixed to 256 bits. So the traditional approach is to use a function called SHA-256, which takes any input and maps it to 256 bits. Hashing, and this is cryptographic hashing, so it has particular properties which are interesting. Basically, it's collision free. So for any two inputs, it's very unlikely that they map to the same output. It's a one-way function. So if I give you the output, the hashed value, it's very difficult to figure the origin, the input. So it's a one-way function. And finally, it's puzzle-free. And I'm going to delve into this a little bit later, but briefly, if I give you a string and I tell you, add something to it, concatenate something to it, add another string to it, concatenate another string to it, so that when you hash it, the output has a certain property. For example, the first 10 bits are zeros. It's very hard to do this because these functions are one-way functions. So the only way to do it is to exhaustively try everything. And this is what makes these hard problems, and that's where mining comes in later on. So hashing is used throughout Bitcoin for different reasons. It uses SHA-256, and obviously, if I take 3 letters, A, B, C, lowercase, I hash them into something. If I make a slight change, so instead of lowercase c, I change it to an uppercase c, I get a completely different string. So knowing the answer to one hash value does not help you figure out another one. So that's the combination function. So whenever we combine, we use the SHA-256 to give me back a 256-bit string. Let me talk about double spending, because that's important in the world of cryptocurrencies. So traditionally, we use concurrency control. So instead, what we could do is, if Alice has, let's say Alice gave Bob some amount of money, and now Bob could, since it's just a string, he could just copy it and make 2 copies of it, and then attach Diana's public key to one of them and Marty's public key to another one, and then sign them and then send them out. Now, Diana's going to give him her car, and Marty's going to give Bob her ring, and we are lost. You know, he double spent the same amount of money to buy 2 different things. We have to avoid this. Concurrency control would avoid this in traditional databases. So one simple way to do it is to say, well, there's some centralized authority. If I have 50 Bitcoins, I go to Trent. Trent is the authority, and Trent checks, does Bob have enough money or not? Does he have enough money to transfer 20 Bitcoins to Diana? Well, he has 50, so then it's okay. So what Trent would do is would split up Bob's money into 30 that is returned to Bob and gives 20 to Diana. That would work. But this is the old solution of banking. And remember, we're trying to avoid banks. We're trying to avoid having this trusted third entity that can help facilitate financial operations. So this is the traditional approach. So what we want to do is to use, or what Bitcoin wants to do is to use a decentralized approach. And basically, we're going to use a ledger, a blockchain, which is going to store all this information and is then eventually going to avoid double spending. Let me delve into this more. So what we need is all the Bitcoins are going to have to agree together on what is the order of transfer operations, all the different transactions that are being executed in the system. They have to agree on it, and they have to verify that everything is consistent to avoid double spending and to avoid underspending and all of these problems. So we're going to distribute all this. So we're going to create a ledger. What is the ledger? It is the blockchain. So now we can talk about blockchains. And basically, a blockchain is a linked list where each node in the linked list is a block, and the block has a bunch of transactions. So you have the first block has a bunch of transactions, second block has a bunch of transactions, and as the system evolves, you have more and more blocks, and all of these are the transactions, the transfers that are occurring in the system. Like in any good old linked list, we have pointers from one node to the previous one. So there is a linking between all of these. Now we want to make sure that this block is tamper-free. Remember, this is a linked list that I'm going to give to each of the peers in the distributed system. So we have lots of copies, and we are giving it to people we don't necessarily trust. So we want to put constraints on it. So what do? The pointers are not only pointers, but they are what's called hash pointers. They basically contain not only, so whenever you have a hash pointer, you have a pointer to the previous block, and you have the hash of the previous block. It's really the header of the previous block. I'm going to explain this in a few slides. But basically, you tie the pointer with the hash of the information in the relevant information in the previous block. And hence, it becomes very difficult to change anything, because if somebody changes these two black transactions to red transactions, then the hash value is going to be wrong. So if I want to fix this, I'd have to really fix a lot of hash pointers. And these hash pointers are functions of computationally expensive operations that are going to be in the content of the block. So it becomes extremely hard. It's not saying it's impossible, but it's very hard. And in general, this is the attitude of these high cryptocurrencies, especially the permissionless or public cryptocurrencies, is they probabilistically guarantee things. It's very hard to, it's not, we are not sure 100%, but we are probably there most of the time. So the big picture is I have nodes scattered all over the world. This is the peer-to-peer Bitcoin network, and each of the nodes has a copy of the blockchain. Okay, why are we doing all this? To execute transactions. So what we want to do is we want to add a new block. This is what you do with any interesting linked list. You want to insert a new block, basically, a new node. So what we have to do is we would like to add a new block at the end of this blockchain. We need to verify that it is not conflicting among itself, among all the transactions in this block, and also with the transactions that are in the previous blocks, so that it is consistent. For example, that Bob actually has the 50 Bitcoins that he claims he wants to transfer 30 of. So we have to make sure that he really has the 50. So this is not too difficult. We can, if I have a copy of the blockchain, you are all computer scientists, you know how to traverse a linked list and figure out if this is consistent or not. We can try to do it more efficient, but basically it's not too difficult. What is critical is how to make sure that all the different nodes that were scattered all over the globe that have copies of this blockchain agree on the next block. Okay, we want to make sure that all the different copies agree that the next block is the one that I'm giving you. Maybe there's another competitor, maybe somebody in Brazil is sitting, Fabio sitting there and wants to add his own block. So both me and him want to add a block. How do we make sure that one of us ends up adding? Neither of us is necessarily malicious. I'm doing my work and Fabio's doing his work, and we both want to do it. This is an age-old problem in distributed systems called consensus or agreement or Byzantine agreement. Byzantine agreement is basically agreeing, or consensus, agreeing among the number of participants on one particular thing. In this case, it is agreeing on the next block. The question is, do I know all the participants or not? Traditionally, consensus, Byzantine agreement, distributed systems, consensus assumed in all the time that we know N. We know the number of participants. The room now is locked. Nobody can come in, nobody can go out. So the question is, do we know it or not? And in the blockchain world, this is where there is a bifurcation of the community between public and private, permission and permissionless. So in the permissioned private environment, we have a bunch of people, individuals, who all know each other but do not trust each other. But the number of individuals is known. So in a database setting, this is, for example, a supply chain. We know who is producing the product, who is transferring it, and who's consuming it. But the individuals in this process do not necessarily trust each other. So here we can use the traditional Byzantine agreement protocol, for example, practical Byzantine agreement, and that has been used in various different systems, Tendermint, Hyperledger, Fabric, and Mohammed is going to talk more about that later. Or even it could be Crash. And this becomes very similar to things we are familiar with, except that we have this log as a first-class citizen. So we could even use a protocol like Paxos, which is just assuming crash. So this is if we go the permissioned world. However, if I don't know the number of participants, then we need something different. We need a new approach to address this. And this is where Bitcoin came up with this notion of mining. Basically, you want to replace communication. I don't want to communicate. I'm going to replace it with computation. I'm going to solve a difficult problem by myself without talking to anybody else. And if I solve it first, I win. I am going to have the right to add the block to the blockchain. So it's in the permissioned world, using consensus protocols, you communicate, you get a majority. This is what we do in an election. We vote, and if somebody gets a majority, in most countries at least, if you get a majority, then you become the leader. In this case, we're going to replace this communication with computation. And so there are different approaches, for example, proof of work, and that's what I'm going to be talking about in Bitcoin, and that's often called Nakamoto's protocol. Nakamoto is the one who, supposedly this mystical person who invented Bitcoin. Or you could have proof of stake, which is another version which has been used in various different protocols like Peercoin, Ethereum, and even Algorand more recently. So let me go a little bit into permissionless and how we're going to do this mining process. So let's focus on one process that is trying to add a block. So let's call this process the miner. And we have a whole bunch of clients, and there's the blockchain. Every time a client issues a transaction, Alice transferring money to Bob, they send it to the miner. They actually broadcast it. They send it to any miner. So this goes, it's a lazy propagation gossip kind of algorithm. So it propagates through the system. If I'm a miner, I get a transaction, I put it into the blockchain, and I keep on adding. So as transactions come, I keep adding these to the blockchain. And what I want to do is I want to be able to add this blockchain to the blockchain. So what do I need to do? I need to verify that they are all consistent with each other. If I succeed, then I'm going to get some money as a reward for my hard work in this mining process. So we call this the reward. So there's a reward that is issued, and the reward is given to me. And this is how new Bitcoins are created. Lots of interesting things that we can talk about. But let's look at the block. So up till now, I've been giving you this illusion that it was only transactions. Well, really, there is the content, which is the transactions, and also there's a header. The header has a lot of important kind of bookkeeping things. A Merkle tree, which basically captures the content. And critically, we have a nonce. The nonce, N-O-N-C-E, which is basically a string. And this is what is the responsibility of the miner, to figure out the nonce that is going to be added to this. Let me talk more about the nonces. You want the nonce, the string, so that if it's appended to the rest of the header, after you SHA-256 it has a certain pattern. It has a value less than something, less than a difficulty D, which is actually also specified in the header. So let me do this a little bit more. So the output of SHA-256, remember, is 256 bits. The D specifies the difficulty bits. So you want the leftmost bits, D of them, to be 0, to all of them to be 0. The difficulty is adjusted every 2 weeks to make sure that it takes about 10 minutes to solve this problem. So finding the nonce. Let me illustrate. Remember, SHA-256 is one way. So I cannot just say, oh, I just figure out it immediately. So the only way I can do it is to exhaustively try different nonces. So here is an example of a header which gives you the version number, etc. So it's basically a string. And what I want to do is I want to add something to the place of the nonce to make sure that when my target is to have 18 zeros at the very beginning. Let's say that this is the difficulty, 18. So what am I going to do? I'm going to start by putting a nonce of 0. Okay, I can start with anything, it doesn't matter. I get the output, so I concatenate 0 to the string of all the rest of the header, and what do I get? I get this string. Does this string look like it has 18 zeros at the very left? No, it doesn't. So I'm very sad. I didn't win. I have to try again. I'll try 1. I could have tried something else. I get this string. It has no zeros. I try 2. I'm a little bit luckier. I have a few zeros, but they're only 7. Nah, not good. I keep on doing this until I end up with this string, which gives me 18 zeros, and this means I have succeeded. So now my nonce is what you see, this green string, and that is when the miner succeeds. And typically it takes, it's designed so that it stays about 10 minutes for every calculation. So now we have, when you have a new update, what you need to do is you're going to mine, and there are lots of other miners that are going to be trying to do the same thing. And they will, if I succeed, I'm going to broadcast it to everybody. And this is how the blockchain is created. Obviously, it is possible that both me and Marta might actually succeed at the same time in figuring out nonces. As I said, everything is probabilistic here. So it is possible that there are, and this is what's called a fork. So you might have a green miner and a red miner, and you might end up with forks, and forks might have conflicts between them. So Bitcoin has to come up with a technique that makes sure that forks do not survive. So what do? They have a rule that miners always try, it's a rule of thumb. Miners always try to join the longest chain. And so once one chain is longer than the other, more miners are going to follow up on this. As a result, the shorter chain is killed, is eliminated, is aborted. So all the transactions in that shorter fork are lost. And they obviously have to be retransmitted, etc. One thing that we worry about is attacks. Is it possible? And Nakamoto's first paper actually specifies that, yes, there is a possibility of attack if a majority, 51% of the participants in the network cooperate with each other, they could actually cause forking and can cause problems. And this is bad because it can cause double spending. For example, you might have this green block that was added. It refers to something that was spent earlier on in the blockchain. And then what the bad guys do is they fork. Because they have more power, they're going to add more blocks, and they create a longer chain. And now the question is, when is transaction 2 going to be aborted? So now this causes a problem. When do I know that what I have transferred is actually committed in a database sense? And what Bitcoin does is it says that once a transaction is 6 deep, and the depth can depend, one can do a lot of interesting calculations to figure out how deep you want it to be. And I think Victor might talk about this a little bit more in the next slides or two. But basically what Bitcoin does is it says, when it's 6 deep, then it's very unlikely that there will be a branching. And this is when you consider it committed. So in general, you have high latency. You have very low throughput. Remember, I'm allowing you to add 1 block. In Bitcoin, it's 1 megabytes of per 10 minutes. So that's about 7 to 6 transactions per second. So this has all been criticized. The consistency guarantees are probabilistics. There is no notion of privacy up till now. All I've talked about is digital signatures, which help you to enforce things. Transparency is there. And there's a lot of loss in energy. We've heard a lot how proof of work actually consumes more energy than countries like Iceland, etc. So what I'm going to do is I'm going to stop now. I'm going to give over to Victor. And what he's going to do is he's going to continue in this permissionless world and show you that how by doing sharding, I might be able to improve performance and how we can actually use permissionless blockchains to exchange coins across different currencies. Then Mohammed is going to talk about permissioned blockchains, so private blockchains, and then we'll end with Sujaya, who's going to tell us some of her recent work on taking the ideas of blockchain to help develop databases in an untrusted world. Fabio has a question.
Oh yes, Samer. So could one miner like create dummy transactions to fill in its own working page and so finish like earlier than others, and then with that achieving, you know, eventually the work done before the others? Would that make sense?
Yes, so there are two ways to answer this question. So the quick answer is, well, if it's going to create dummy transactions, who is it giving it to? But you could tell me I'm giving it to my friend, so that's okay. So there's a particular attack that was developed called selfish attacks. And in selfish attacks, and this was developed by a group at Cornell, where they basically, I am going to help myself by giving myself a head start. It turns out that this can be beneficial if a third of the processes are malicious and cooperate with each other. So I would point you to that work, which is very interesting. And it shows that the 51% attack is assuming certain assumptions, but there are other assumptions that require actually at most a third to be bad.
Thanks.
Sure. So why don't I give it to Victor now? Or if there are questions, whatever. Yeah, I'll give it to Victor and he can take over. So I'll stop.
Are you guys listening to me? All right, I just have a small question.
Yeah.
Is there any notion of querying the log? I mean, it's...
Yes, so everybody has the log, and so you can actually ask the log,
right.
and the miner has to ask the log, has to verify everything. So this is integral to the process. Yes, very good point. Yes.
So is there any data structure special organized for random query, or not really?
Victor, do you know?
Like, are we looking for a data structure to
make it more quicker?
Yes.
Maybe Ethereum has something.
You could verify if the transaction is included in a block or not using the Merkle tree. So all what you have to do is, because the way the Merkle tree is ordered is that basically you put the transactions one after the other. So this is transaction 1, 2, 3, 4, 5, and then you hash all the way. So if a client wants to verify that TX1 is actually included in this block, all what you have to do is to have the siblings of this transaction along all the root, until the root, and just verify that the root is included in the header and that the root is correct, like the header is correct, correctly mined. So that's how you could verify if a transaction is included. But if you want to go back without scanning all the blockchain, I'm not sure. There must be some data structures, but I didn't look into that.
All right.
Yeah.
Okay. Thanks a lot.
Yeah, I want to add something to what Fabio asked to Amr. Yes, you could mine dummy blocks and you only include the reward transaction on them, the only thing here is that the cost of mining this block is as expensive as mining a block that is full of transactions, because we are searching in a random space. So what would give you incentive to accept other people's transaction is that you would take a fee on this transaction. So this is an economic incentive here, that once these transactions are added, you are getting a fee in addition to the reward that you are mining.
I was thinking about time. So the time that would take to receive all the transactions that are going on. And if I can do it quicker, so if I have partially filled block, I would fill the remaining without waiting for the transactions to come. That's what I had in mind.
That's the point that I was mentioning first, is that the cost of mining a block that in terms of time, the cost of mining a block that has only the reward transaction is as expensive as when you add the transactions, the incoming transaction. And the reason is the search space is huge and we are doing random guesses. So basically, you could do 10,000 random guesses and you get a transaction. When you include it, you have to start over, right? But it doesn't matter.
You're starting before, right? Than the others. It's like
so you don't have to,
it's like
Fabio, you don't have to even wait to fill the whole block. When I get one transaction, I can start mining immediately.
Okay, so that was my misunderstanding. Thank you.
So
got it.
What's happening actually in the mining is that you put the reward transaction, you start mining. And then you get a transaction, you include it and you continue mining. You get another transaction, you include it and continue mining. Because the probability of finding a solution when you have two transactions is as equal as finding a solution when you have one transaction or zero. So that's all. But you cannot.
Why don't you start, Victor, your talk?
Okay. But you cannot start mining a block. So you cannot start. Hold on. I want to share screen. Which one? Yeah.
Just reminding you guys that we have, still have an hour to go, a little bit more.
Yeah. So I will just do this very quick, but just to finish the point is that you cannot start mining upcoming blocks because each block depends on the previous block. You have the hash of the previous block. So you can't start 20 until you have 19. That's all. Okay, so I'm going to cover, so Amr ended on the note that we have, can you all see my screen? It's all good? Yeah, okay. So what Amr said is that the throughput of open blockchains is very small. We are doing 3 to 7 transactions per second, and people are saying, okay, we're going to take over the world with this system, but this cannot scale to support the world level of transactions. We're having Visa does on the average like 20,000 or something, and in the peak it could go into up to 80,000 transactions per second. So you cannot replace this system with that one, even if you get all the trust guarantees and everything. So what we are trying to do here is to look at this scalability angle and at the same time cross-chain transactions. What would happen if we do cross-chain transactions? So I'm going to start first by saying that we could use sharding as a scalability solution. So if we think here, we have the blockchain and you have the coins, you could split them into ranges. If you say, okay, I have 21 million coins in the Bitcoin example, we're going to say that the first, the 0 and 4 and 8, the coin numbers that are divisible by 4 are in the blue shard, and the ones that are divisible by whatever one, like we are doing 0 and like anything modulo 4 equals 0 is in the blue shard, anything modulo 4 equal 1 in the green shard, and so on and so forth. So instead of having the network maintaining all the blocks of all the coins, what we can do is to say, okay, we're going to split this and split the nodes as well. And what we're going to end up having is we will have kind of 4 independent blockchains where some nodes are mining the blue shard, some nodes are mining the green, and so on and so forth. But then that comes with 2 types of transactions now. Previously, if you want to transact over any of these shards, all the nodes maintain a copy, but now we don't have a copy of everything. So what we could face is We could have a single shard transactions, which is typical. It's pretty much similar to the transactions that I'm just explained. The miners know the coins on this shard, so they can you can process this transaction. And we could have cross shard transactions, which is I want to transfer some money from the green to the blue. What do we do? And that would require something like atomic cross shard commitment protocol. Or to generalize, since we have many blockchains, we need atomic cross-chain commitment protocol. And if we look at the landscape right now, we have thousands of blockchains and tokens, and users now can buy these tokens using US dollars from exchanges. You can do direct token transaction in one blockchain using the transactions that Amr just explained. However, we don't have yet a correct support for direct token transactions across blockchains. And for example, Alice wants to swap X Bitcoins for Y Ethereums. These are two blockchains. No miner maintain the copy of both Bitcoin and Ethereum network. So how would we do that? And this is really important because, I mean, if we look futuristically, if we want to store property assets or ownership of assets in these blockchains, we will need support. Like if we have the housing blockchain where everyone's house is stored in the blockchain and we want to sell this house for a Bitcoin, we need to find a way where the Bitcoin network and the housing network can communicate. So this is what we call cross-chain transaction. So it could be to facilitate such transactions or to scale a single network blockchain through sharding. So let me give you an example. So assume that we have Alice and Bob, and Alice want to swap X Bitcoins with Bob for Y Ether. So the visual representation of this is that Bob has Y Ethereum and Alice has X Bitcoins. And they want to run this transaction such that, I want to move the view is,
It looks fine to me.
I'm unable to see the videos are on top of the presentation. But anyway, yeah. So Alice owns X Bitcoins and Bob owns Y Ether, and they want to swap them. So what we want to do is, after we run an atomic cross-chain commitment protocol, is that the ownership of the Y Ether in the Ethereum network moves to Alice, and the ownership of the X Bitcoin in the Bitcoin network moves to Bob. And that has to be done atomically. So notice that the miners of each of this network don't communicate with each other and don't have a copy of the other blockchain. So I'm gonna cover a building block here, which is smart contract that we will use in this protocol. And you can think of a smart contract as a stored procedure that runs, that could access the data of one blockchain. It does not access the data of other blockchains. And it has a set of functions, and these functions will be executed on the data and alter the state of the data once some conditions are met. So for example, they are like classes in object-oriented programming language. You instantiate an instance of the smart contract in the blockchain. So you could think of that instance as an object in the blockchain, and it allows end users to store generic data objects in the blockchain, define functions that manipulate these data objects. These smart contracts have attributes that could represent a car or a house, and they have functions like rent and buy, and can be used to implement generic logic. And the reason smart contracts are important is that you could represent your house inside the blockchain and say, I want to sell it using the tokens of this blockchain. You can do generic logic, like you can lock assets in the blockchain in some condition or something, and transfer the ownership on some conditions. So this is very important building blocks that we're going to use. So an example is, we say that we have this smart contract. We instantiate an object of it where the sender is Alice, and the recipient is Bob, and the asset is X Bitcoins on some condition that if a secret matches the hash of the secret H, we do this transfer. So is that clear? So far, so good. So anyway, so I'm going to move on to the atomic swap protocol, which was presented by Nolan in 2013 in a blog post and was formulated and generalized by Hurley in 2018. And this protocol was trying to solve the same problem we're talking about, but they fall short in some aspects. So let me just go over it very quick, and then we'll explain our protocol afterwards. So Alice wants to trade Bitcoins for Ethereum with Bob. So what does Alice do? She basically creates a secret S.
And just to remind people, Alice and Bob don't trust each other. Yeah, it's very important. You're living in a world where nobody trusts. They still want to do a transaction together.
Yeah, and the other thing is that they want to do transactions across blockchains. So Alice would create a secret S and calculate the hash h, small h, of this secret using a known hash function, let's say SHA-256. So Alice will keep both the secret and the hash to herself, and then say, okay, I'm going to write a smart contract that locks X Bitcoin of mine and move them to Bob if Bob successfully provides the secret S to this smart contract. Okay, and I'm not going to put S in the smart contract. I'm going to put the hash H such that small h equal to the SHA-256 of the secret that Bob is going to provide. Then I'm going to take SC1 and deploy it in the Bitcoin network. So that's now an object in the Bitcoin network, and everyone can see it. When you can see it, you can verify actually that the destination of this smart contract is Bob. You can also verify that the amount of Bitcoins transferred in this smart contract are X. And you can verify, you can learn about small h, which is the hash of the secret. No one knows about the secret so far except Alice. Now, once H is made public, Bob is going to take this H and create another smart contract in the Ethereum network that says move Y Ethereum to Alice if Alice provides a secret S to this smart contract. Same way. And Bob is going to deploy SC2 in the Ethereum network. And we could see in the Ethereum network once this contract is published that the destination is Alice and the amount is Y Ethereums, and it is logged on the hash of a secret that is equal to small h. Now, what's going to happen is that if Alice provides S to SC2, SC2 is going to hash S and compare it to the H, small h that was provided. And if they are equal, the smart contract is going to move the ownership of the Y Ethereum from Bob to Alice. But once S is revealed, Bob should be able to take S and put it in SC1 and claim the X Bitcoins. So what can go wrong here? So the main problem here is, so that this is a nice protocol, it's very good, but it has a very important problem here, is that these assets are logged forever until they are unlocked with the secret S. And they are always unlocked to the destination of the asset. So SC1 will only unlock the assets to Bob, and SC2 will only unlock the assets to Alice. Now, what could happen here is that Alice locks her X Bitcoin in the Bitcoin network through SC1, and Bob sees SC1 but refuses to publish SC2. So now what happened is Alice lost her X Bitcoins for good, because if she puts the secret S in the smart contract, she basically will give the money, free money, to Bob. So a conforming party to the protocol ends up worse off because Bob does not follow the protocol. So the prevention that was used in this protocol is to use time locks to expire the contracts and specify an expired contract should be refunded to the source of this contract. So now, once we use time lock, we depend on the notion of time. That makes the protocol actually synchronous. And that faces a lot of problems that we will address very soon. So doing the time, what we are going to say here is that Alice is going to add a condition to SC1 that says refund SC1 to Alice if Bob does not provide the secret S to SC1 before 48 hours. Say some time, like 48 is just an arbitrary time. It's not very arbitrary, but it's just a value for now. And then Bob is going to add the same condition to his smart contract, but saying refund the Y Ether in SC2 to myself if Alice does not provide the secret S within 24 hours. And the choice of the 48 and 24 are very important here. So this is a visual representation, Alice on time, and you see we divided the time into 4 deltas where each delta is 12 hours. Alice creates the contract, it gets announced, Bob sees it and creates the contract, which is the red one. And then the end of the red contract is the red circle, if you can see here. And the end of the green contract is the green circle. And the important thing here is that the red contract has to reside inside the green contract, the time of it. Otherwise, if the red ends here, somewhere here, what's going to happen is that Alice can wait until the green expires and she gets refund, and then she redeems Bob's asset here. So that's the logic behind it, is that you have to put the contract one inside the other. Now, what can go wrong here? Basically, the normal execution is that Alice will put the secret here, redeems the X Bitcoin, the secret is revealed, Bob will take it, and Bob has 1 delta time, which is like 12 hours to redeem his assets and make this transaction work correctly. But what can go wrong here is that if at this moment, when Alice redeemed the Y Ether, Bob fails or faces a network denial of service for a delta time, you could say 12 hours. What would happen here is that Alice's contract will expire, and Alice will take both the Y Ether and the X Bitcoins, which is in some sense, we're saying it's atomic swap, but it's not atomic. So this is an atomicity violation. And the main problem here is that using time locks leads to this atomicity violation because it cares about liveness over safety. So we propose atomic cross-chain commitment protocol. So our atomicity-based approach is pretty much similar to 2PC. Is that the decision of both transactions has to be taken at the same moment, atomically, and then both transactions has to follow this decision. So the decision is made atomic, and they either both commit or abort. And the transaction cannot commit or abort until a decision is reached. Let me give you a building block that we're using in our protocol that will help us explain it. We want to answer the following question: how can the miners of one blockchain verify the transactions that are taking place in another blockchain without maintaining a copy of this blockchain? And the way we do that is that, let's assume we have a verifier blockchain A that want to verify that TX1 is going to take place in a verified blockchain B in the future. So what we do here is that we go D blocks in blockchain B and get the header. In that sense, the header is the red header. And the reason we choose D blocks deep, as Amr mentioned, is that as the block gets deeper, it becomes stable. The probability of forking at this block is negligible. So we choose a D block, we get a header of a block, of a stable block, and put it in a smart contract SC in blockchain A. So we get the header only. Now, what we are going to do is to wait until TX1 that we want to verify take place in blockchain B, and it becomes stable after D blocks. And then I want to prove to the miners of blockchain A that TX1 took place in blockchain B. So what do? Is take evidence of TX1 from blockchain B and give it to the miners of blockchain A. That evidence consists of all the headers starting from the red header that we included in blockchain A smart contract up until the block that has TX1. So we include that block, and then all the headers that follow. And we send this to the miners of blockchain A, and the miners could verify actually that TX1 took place in blockchain B. So how would they do that? We want to verify that each header includes the hash of the previous header, which is a condition that it took place in this blockchain. Now, the other thing is that the proof of work of each header is correct, which means that actually these blocks are legit blocks and they have been mined, which means that a lot of work has been put to mine them. And then the TX1 is included and correct, according to some agreement we put in the smart contract, and that TX1 is buried under D blocks, which means it's stable enough. Now, one could ask, how would we guarantee that this is actually an evidence that is taken from the actual blockchain, blockchain B? And there's no guarantee. The only thing is that it's economic incentive. The cost of generating 2D+1 blocks where TX1 takes place in block D+1 that are valid after the red block that we included from the actual blockchain, this cost, we choose D such that the cost is much more than the gain that you could get from TX1. And if that's true, a malicious user has no incentive to create fake evidence. We might as well just use the actual evidence. So Atomic Cross-Chain Commitment Protocol, the AC3WN, we propose, this is our protocol. It's Atomic Cross-Chain Commitment Protocol that uses a witness network. So we use another blockchain to witness the atomic swap, which is similar to the coordinator in 2PC. So the witness blockchain decides the commit or the abort of the swap. And once the decision is made, all sub-transactions in the Bitcoin and Ethereum network has to follow this decision, and it achieves atomicity, either all commit or all abort. So the cross-chain verification, as I just explained, is leveraged twice. Miners of the witness network verify the publishing of contract in the asset blockchain, and miners of the asset blockchains verify the decision that is made in the witness network. Notice that the witness network is an open blockchain that could be actually one of the asset transfer blockchains. So you could use Ethereum to coordinate a transaction across Ethereum and Bitcoin, and so on and so forth. So this is an outline of our protocol. Basically, the user deploy SCW, which is, we call it the smart contract of the witness, and put it in a state published. And in that, so the blockchain, the witness blockchain is the verifier in this case. In that, we want to verify that there are two smart contracts or two transactions that are going to take place in the Bitcoin and the Ethereum blockchains. So what we do is that we go into a stable blocks in these two blockchains, include the headers in SCW. Then we wait until SCW is stable, and then we go into the Bitcoin and Ethereum in parallel. We don't have to have sequential execution unlike the atomic swap. And we say, okay, I'm going to deploy SC1 and SC2 such that SC1 will transfer the X Bitcoin to Bob if SCW state is redeemed, and refund them to me as Alice if SCW state is refunded. The same with SC2. SC2, Bob would say, move the Y ether to Alice if SCW state is redeemed, and refund them to me if SCW state is refunded. And I'm going to include the header of the block that has SCW and SC1 and SC2. Now, once SC1 and SC2 are stable under D blocks, one could say, okay, now I have evidence that both parties of this distributed transaction voted yes on this transaction. So their deployment of SC1 and SC2 is similar to voting yes in 2PC. So I can take an evidence starting from the headers that I included in SCW up until D blocks after the deployment of SC1 and SC2, and take them to the miners of the witness network. They could verify that SC1 and SC2 are valid according to our agreement. We signed some agreement and put it in SCW. The details are in the paper. And then once this is verified, we can move the state of SCW to redeem. Once the state is stable after D blocks, anyone could take this approve from SCW smart contract from the witness network to say that this distributed transaction is committed, and that can be used to redeem the assets in both SC1 and SC2. So in our protocol, SCW state determines the commit, either redeem, or abort, either refund. That's the abort decision. And once the state of SCW is altered and it becomes stable under D blocks, if all the sub-transactions in this distributed transaction must follow this decision, because that's coded in their smart contract. And none of the sub-transactions can decide on a different decision, because still that's coded in their smart contract. Even if a participant fails or faces a network denial of service, which was the problem with the time locks, when they wake up, the evidence still exists in the witness network, so they can redeem their assets later. The only way to violate atomicity is to fork the witness network, is to say, okay, I'm going to create an alternative evidence. But as we mentioned before, we make the cost of this alternative reality much more expensive than, so the choice of D guarantees that the cost of generating that is much more expensive than the gain that you will achieve. So economic incentive would prevent that attack. It's very important that even the atomic swap could face this attack. Like someone could fork the Bitcoin network before the deployment of the smart contract that transfers the assets. So it's actually an attack that would happen on any of these protocols. If we look at performance, so the atomic, our AC3WN versus the atomic swap, in the atomic swap, since we depend on time locks, and we depend on that one of the participants is the coordinator, in our example was Alice. Alice has to deploy the smart contract first to give Bob the confidence to deploy his smart contract. And then if there is Carol, so Bob is transferred something to Carol, so Carol has to wait for Bob to deploy his smart contract. So it's more of like linear with the diameter of the graph. While in our case, all the participants are waiting just on the deployment of SCW, so they can deploy their contract and redeem them in parallel. So in our sense, it's our latency is fixed. It's 4 deltas, while the atomic swap starts at 4 if the graph is swapping among 2 participants, and it goes linearly with the diameter of the graph. Also, that our protocol is more general. It covers like, yeah, I'm gonna cover this very quick. It covers like disconnected graphs and other things, and you can see all the details of this in the paper. Finally, this happens with adding the extra cost of deploying the witness network smart contract. To summarize, we presented AC3WN, which is the first safe atomic cross-chain commitment protocol. It has a constant latency regardless of the swap graph, and it adds a slight deployment overhead in terms of the dollars, which is the cost of deploying the witness network smart contract, and it can help in solving scalability and cross-chain transactions. And with that, I will hand it over to Mohammed to cover permissioned blockchains. Thank you.
So I just want to conclude by saying that this paper was presented in VLDB last month in Japan. And in the same session, Maurice Hurley, Liba Liu, and Barbara Liskov presented another result which has to do with cross-chain deals, which is kind of similar. So there's a lot of interesting cross-chain and cross-research interactions here that I would encourage you, if you are interested, to look at all this work. What we're going to do now, unless there are specific questions to Victor, is to move on to Mohammed. And if you lost Victor in the middle of all the details, it is a complicated protocol, don't worry. Mohammed is going to start on something completely different. It's permission blockchain, so it's a different environment, and I hope you can follow him now. So Victor, please stop your sharing. Yeah.
I just wanted to know if anybody has any question to Victor or... Okay, so we can go on.
So, okay, can you see my screen now?
Yes.
Yeah, it's okay.
Okay, so thank you for the third part of the talk is about permission blockchains. So we had talked about like cryptocurrencies like Bitcoin and Ethereum, but one question is, does blockchain have any applications other than cryptocurrencies? For example, can we use basically blockchain in like seafood supply chain, where we have different passes from the environment resources to end consumers, such as recreational fishing, commercial fishing? And can we use blockchain to say basically we can use, for example, IoT-enabled sensors to to tag seafoods, and then these sensors are going to continuously transmit location and time on blockchain. And at the end, the buyer can access a comprehensive record of the fish's provenance. Actually, the answer is yes. And in the domain of blockchain, we have Bitcoin and Ethereum, where, as I mentioned, in such cryptocurrencies, anyone can participate without a specific identity. On the other hand, we have distributed applications or large-scale data management applications, such as healthcare, such as the supply chain management, where participants are known and identified. In the context of blockchain, we call these systems permissionless, and these systems permissioned blockchain. The focus of this part is on permission blockchain. A permission blockchain can be defined as a set of known identified nodes that might not fully trust each other. So, but permission blockchain has unique features such as transparency, provenance, authenticity. But on the other hand, distributed application, or let's say larger scale data management application, have their own requirements. For example, in a financial applications like Visa, we want to process tens of thousands of transactions within a second. So we need high performance. In supply chain management, we have collaborators, we have enterprises that they want to collaborate with each other, but they don't trust each other and they don't want to share their data with each other. So we need confidentiality. In large databases, we need a scalability. And in crowd working environment, we might want to verify an action has been performed by some participants in a privacy preserving manner. So we need verifiability. And in all these applications, all these distributed applications, we need fault tolerance for high availability. So we can say a large scale data management application needs these 5 basically requirements. And in this talk, I'm going to mostly focus on performance and scalability aspects. Before that, I'm going to briefly basically introduce consensus problem in the domain of permission blockchain. Consensus is the main building block of blockchains, and in consensus problem says we have a set of distributed nodes and they need to reach agreement on a single value. Nodes might be crash only or Byzantine, that means might behave maliciously, and the system might be synchronous or asynchronous. Blockchain is an asynchronous system. So I'm going to introduce 2 of the most known consensus protocols, one for crash only nodes and one for Byzantine nodes. Paxos is for crash nodes. In Paxos, we assume that we have at most F concurrent crash failures. So if we have at most F concurrent crash failure, we need to ensure that a message has been replicated on at least F+1 nodes. Why? To ensure that there is at least 1 correct node. So we call this F+1 a quorum of replicas. And we need, and any 2 quorums of replicas need to intersect on at least 1 node to basically to ensure that if there is we made a decision here, there is some node that is aware of that decision. So we need intersection to be 1. As a result, the network size becomes 2F+1. In Paxos, we have a leader election phase. And once the leader is elected, the leader sends a proposal to all backups. And then backups, once they receive the proposal, they send their votes back to the primary or to the leader. So we have 2 phases of communication. One is proposal, and then we made the decision based on the votes that we have. Another protocol is PBFD. PBFD is for Byzantine faults. In PBFD, again, we can assume that we have at most F malicious failures. But here, the quorum size is 2F+1. Why is that? Because we want to ensure that correct nodes outnumber the faulty nodes. Note that here, faulty nodes are not crashed. They are alive and they participate in the protocol, but they can clone and send they basically behave maliciously. So we need a correct node to outnumber faulty nodes. So if there are F faulty nodes, there should be at least F+1 correct node. As a result, the quorum size becomes 2F+1. And the intersection of any 2 quorums needs to be f plus 1. Why? Because f of them might be faulty. As a result, the network size becomes 3f plus 1, 2f plus 1 each quorum and f plus 1 in intersection. So the network becomes 3f plus 1. In PBFT, again, we have the primary who sends proposal to all backups. But here we have a proposal validation phase. Why do we need that? Because the primary might be malicious and might send different requests or same request with different sequence number to all nodes. So nodes need to talk to each other to ensure that they have received the same proposal from the primary. This is an end-to-end communication because we don't trust anyone. So we all need to talk to each other to ensure that the primary is non-faulty. And once we validate the proposal, nodes are going to make decision. Again, the decision making is end-to-end communication. Why? Because there is no single node that is trusted. So nodes again need to talk to each other to ensure that they agree on the decision. So again, we have two phases of ON square communication. So you can see that in the presence of Byzantine failures, the protocols become expensive. So with that introduction, I'm going to talk about blockchain performance. Early blockchains like Tendermint, like Quorum, they use an order execute architecture. In the order execute architecture, clients send their request to an ordering service. Ordering service includes enough number of nodes to order transactions. For example, if nodes are Byzantine, then we need 3f plus 1. Here, for example, we have 4 nodes. That means f is 1 and we have 4 nodes. Nodes are going to order transactions one by one sequentially. And once the block is completed, they are going to send the block to executor nodes. Note that this ordering nodes and executor node could be the same, but we separate them here. So executors are going to execute transactions again one by one from the block. So we have a block of transaction. The block might have hundreds of transactions, and then they are going to execute these transactions one by one. And once all transactions are executed, they are going to append the block to the blockchain ledger. So the problem here is sequential execution of these transactions. In Hyperledger Fabric, we have a new architecture, new paradigm, which is execute order validate. That means they execute the transaction first in parallel, and then they order transaction. So Hyperledger has 3 types of nodes: client, endorsers, which are basically the executors, and orders. Clients are basically they send transaction to be executed. Hyperledger supports multiple applications. So we can have clients from different applications like blue application, green application, and yellow application. We have endorsers who are going to execute transactions and also validate the transactions. Endorsers basically are the nodes who maintain the blockchain ledger. And each application has its own set of endorsers. And finally, orderers who are going to establish the total order, basically run the consensus among all transactions. And these orders are not going to maintain the blockchain ledger. Note that in Hyperledger Fabric, the consensus protocol is pluggable. We can, depending on the failure model of node, we can use Paxos, we can use PBFT, or any other consensus protocol. So let's see how it works. We have, as you can see, we have clients. We have different applications like green application, blue application, and yellow application. Each application has its own set of endorsers, and we have a set of orders. So clients send their requests to the endorsers. Endorsers are going to execute the transaction. As you can see, we have parallel execution of transaction and send the result back to the clients. We call these results as endorsement. The clients check some endorsement policies. What is endorsement policy? Sorry. Endorsement policy says, for example, if we have 4 yellow endorsers, if we receive matching results from at least 3 of them, we can basically go ahead and execute that. We can go ahead and order that transaction. So if the results satisfying endorsement policy, they're going to send the results to the orders. Orders are going to run consensus on these transactions one by one. generate blocks, generate a block of transaction, and send it back to the endorsers. Now endorsers are going to do the validation, the third phase. We have execute, order, validate. In the validation phase, they basically validate the transaction to ensure that transactions are valid and they satisfy the endorsement policies. And they also check the read-write conflicts to ensure that there is no conflicts between transactions within a block. If everything is fine, they are going to add transactions to the blockchain ledger. But what if the transactions are conflicting? What does conflict mean? It means that we have two transactions that access the same record, and one of them is a write operation. So for example, let's assume this block of these three transactions. Let's assume the green one writes on record A, and both blue and yellow are going to read record A. So there is a problem here. Why? Because all these three transactions have been executed at the same time. As a result, the blue and yellow were not aware of the result of green. So once we check, once we send it to endorser, and endorser validate that, they see these conflicts, and they have to basically mark blue and yellow as invalid transactions because they have been executed on a basically outdated data. So if, as a result, if we have a workload with high contention, Hyperledger shows poor performance. Before going to, there are several ways to handle this issue. I'm going to introduce one of the systems, but before that, let's talk a little bit about dependency graph. Dependency graph is a way to basically expose ordering dependency between transactions. So let's assume we have 5 transactions, T1 to T5. We have read set and write set for each of them. Rho is a read set and omega is the write set. And they are ordered in a block. So T1 is the first transaction, T5, T4, T3, T2. We want to generate a dependency graph for this block. We have T1, and then the next operation, the next transaction is T5. So there is no dependency between read set and write set of T5 and T1. So T1 and T5 are independent. The next transaction is T4. If we see T4, we see that the read set, it reads B, which is already written by T1. So there is a dependency from T1 to T4. The next one in the block is T3. And T3 writes E, which is already read by T5. So there is a dependency between T3 and T5, and there is the same between T2 and T5 because they both write on D. So this is basically a dependency graph for a block. So Power Blockchain is the next system that I'm going to introduce. In Power Blockchain, we go back to basically the order execute paradigm, but once we order transaction, we execute transaction in parallel. How does it? We again have different applications. We have orderers and we have executors for different applications like blue, like green, where executors maintain the blockchain ledger. Executors in Power Blockchain basically are the same as endorsers in Hyperledger Fabric. So clients send a request to the orderers. Let's say we have green application and blue application. They send a request to the orderers. Orders are going to order transactions one by one, generate the block. And once the block is generated, they are going to generate a dependency graph for the block. And then they are going to send the result to the executors. Executors are going to execute transaction and append the block to the blockchain ledger. So let's go through the detail. In the ordering phase, we have clients who send transaction to one of the orderers, let's say the primary orderer. The primary validates the transaction and initiates consensus among orders. They are going to order transaction and append it to the blockchain ledger, to the basic block. They are going to order transaction until the block is completed. We have 3 metrics for that: either reach to a maximal size, maximal number of transactions, or maximal time for creation of a block. Once the block is completed, all nodes are going to generate dependency graph for that block, and then send the new block as well as the dependency graph to all executor nodes. As you can see, we have executor nodes for different applications, for example, for green application and for blue application. They receive this block. They are going to follow the dependency graph to execute transaction. If there is no dependency between two transactions, those two transactions can be executed in any order. If there is dependency basically in the dependency graph, executor need to follow that dependency. So they are going to execute transactions. The blue ones are going to execute transactions of the blue application. The green ones are going to execute the transactions of the green application. And there might be some sequential or some basically parallel execution, depending on the dependency between transactions. And once they all execute the transaction, they are going to share the result with each other. In the next phase, each node is going to check whether the results are the same or not. It is the same as Hyperledger Fabric, where in the execution phase, we need to have some policies, endorsement policy. Again, here we need to ensure that we have all the execution results are all the same. If that's the case, they are going to basically append the block to the blockchain ledger. So if we want to compare Hyperledger Fabric and Power Blockchain, we can talk about non-deterministic execution, and we can talk about high contention workloads. In Hyperledger Fabric, it executes transactions first. Basically, it executes transactions optimistically at the beginning. And if there is any inconsistent result, it can detect that very early and basically kind of abort the transaction before it's going to be ordered. However, it validates read-write conflicts at the last step. And if there is any conflicting transaction, it detects it very late. So it basically affects the performance. On the other hand, in Power Blockchain, we validate non-deterministic execution at the last step. We basically order transaction, execute transaction, and at the end, we are going to check if there is any non-deterministic result. So it cannot support non-deterministic execution very well. However, since it checks conflicts first and basically it generates a dependency graph, it can basically support high contention workload very well. So with that, I'm going to talk about now scalability. So scalability is basically the ability of a blockchain system to process an increasing number of transactions by adding resources to the systems. So indeed, we have extra resources. We want to utilize them, but we want basically the performance of the entire system becomes higher. So in the domain of blockchain, there are different scalability solutions. One class of solutions are basically off-chain solutions. In off-chain or layer 2 solutions, we basically move a portion of the transactions off the chain. There are different solutions like Lightning networks, like sidechain network, where we have a main chain and we have some side chains or like off-chain that are going to process a set of transactions. Another class of solutions are on-chain solutions. In the on-chain solution, we try to increase the throughput of the main chain. There are vertical techniques where we don't increase the number of nodes, but we try to more power to each node to basically enable nodes to perform more tasks. And we have horizontal techniques. In horizontal techniques, we increase the number of nodes in the network. So sharding is a horizontal technique. In sharding, we say, okay, we increase the number of nodes, and then we cluster nodes into different clusters, and also partition the data into multiple shards. Each of the shards is going to be maintained by a subset of nodes or by a cluster, and they can process transactions in parallel. So let's see why we need why we need sharding. Let's assume we have a single consensus routine. We have these nodes that are going to run consensus and order transactions. So there are like 4 nodes. If we add more nodes to the system, the consensus protocol, the consensus routine becomes slower. Why? Because we need agreement from all of them, or let's say majority of them, or if they are Byzantine, let's say 2/3 of them. But so when we increase the number of nodes, the consensus becomes slower. And if we add more and more nodes, the consensus becomes slower and slower. So the idea of sharding is, let's say cluster these nodes into group. Let's group these nodes into different clusters, and each cluster also maintains a shard of data. So these nodes can basically execute transactions in parallel. What if a transaction accesses 2 different shards? Then we need to run some kind of cross-shard transaction between these 2 shards. In Sharper, the network is partitioned into clusters. Let's say here we have 16 nodes, and we partition it into 4 different clusters, where each cluster includes either 2f+1 crash only or 3f+1 Byzantine nodes. Basically, we need sufficient number of nodes to ensure safety, and liveness. So we need 3f+1 Byzantine or 2f+1 crash only. The application data is also sharded. The application data is sharded here, for example, into D1, D2, D3, and D4, and each shard is assigned to a cluster. Note that each shard is replicated on all nodes of each cluster. We also shard the blockchain ledger. So we say that the blockchain ledger is not maintained by any node. Each cluster basically maintains its own view of the blockchain ledger. So let's talk about the blockchain ledger. So we have these 4 applications. They can process their transactions in parallel, their internal transaction, and at some point we might have cross-shard transaction. This block is a cross-shard transaction between these two basically application. And you can see the sequence numbers. Here is 10, 11, and then it has the part of the sequence number comes from here, so 11, 12, and the other part comes from here, so 20, 21, and 22. Note that we can have parallel cross-shard transactions. If the clusters of these 2 is not overlapping, then we can parallelly process them in parallel. And we might have a cross-shard transaction that basically includes all 4 shards. All 4 shards are involved in it. That's okay. We have a cross-shard transaction with basically a sequence number that has 4 parts. So if you see, while this logical blockchain ledger is structured as a directed acyclic graph, each application is still a linear chain. So the blue application is basically 10, 11, these involved in these 12, 13, 14, 15, and 16. So each application still sequentially orders its transaction. So in Sharper, in this work, we say that each cluster maintains its own view of the blockchain ledger. There is no need for the yellow application to maintain these blue transactions. So basically each shard maintains only internal transactions or intra-shard transactions, as well as cross-shard transactions that the cluster is involved in them. So the blue cluster is involved in these 2 cross-shard transactions, so it only maintains these 2, and all its local or intra-shard transactions. We need also to talk about consensus in Sharper. So we have intra-shard consensus for those intra-shard transactions. It is pluggable, and depending on the failure model of nodes, we can use any basically consensus protocol. However, for cross-shard consensus, we need the participation of all involved clusters. If we have a cross-shard transaction where 2 clusters are involved in that, we need to ensure that both clusters agree with the order of that transaction. So we have a cross-shard transaction for crash-only nodes, as well as cross-shard consensus for Byzantine nodes. So in crash-only node, you see there are, for example, two transactions in parallel. So we have propose phase, accept phase, and commit phase. And in each of these phases, for the accept phase, the leader needs to wait for F+1 matching accept from every involved cluster to ensure that all involved clusters agree with the order and then send commit. So it's in the Byzantine case, we have kind of similar to PBFT. However, it needs results from every involved cluster. Again, it needs since there is no single trusted node, we need to end-to-end communication. And here we need to wait for 2F+1 matching except again from every involved cluster, not the entire system. And again, we have commit. We need to wait for 2F+1 matching commit from every involved cluster. So these are the consensus protocol that are used in Sharper for crash only and Byzantine node. With that, I'm going to finish this part and we'll give the token to Sujaya to continue on. Any question? Or?
So what Sujaya is going to give you now is almost the other direction. What she's going to argue is that there are all these nice techniques that Mohammed and Victor have talked about, and they actually can be leveraged in the database world. And so I'll give it to Sujaya now.
Hello, everyone. Good morning and good afternoon, respectively. So yeah, now we're going to, this is the fourth part and the final part of this tutorial. And here we're going to slightly shift our gears and move our attention to databases, specifically managing data in untrusted infrastructure. So before we go, So before we go into go more in detail with this, I want to motivate why is this important? Why should we be talking about managing databases in untrusted infrastructures? So we've seen in the recent couple of years that there have been so many number of data breaches. There was Equifax data breach, there was Cambridge Analytica that created a lot of noise by leaking millions of Facebook profiles, and it also had some political implications to it. And there was a software bug in Amazon S3 that also leaked millions of Facebook records, as well as Netflix and bank records. And moreover, the next step, the next phase in this kind of leaks are not just leaking of sensitive information, but also data sabotage and data manipulation. So the US intelligence chief, James Clapper, said that the next cyber threat is going to be data manipulation. It is not just leaking of sensitive information, but it is manipulation of these sensitive information by these servers that we don't really trust. And hence, that's the focus of this talk is managing databases when we don't trust underlying servers. Now, in most of this talk, we've discussed many techniques and mechanisms that blockchain has deployed where we deal with entities that we don't trust. Now, the next question as a database researcher that we ask is, can we leverage these techniques and integrate it with mainstream databases? So what does it mean to manage data on untrusted infrastructure? So let's say there's a client with some sensitive, it's an application such as healthcare application, which consists of many sensitive records. Now this client does not have their own infrastructure to build a service. So what they're going to do is they're going to rent servers from third-party cloud vendors. Now the client can choose to rent these servers all from the same cloud provider, or it can choose to rent different servers from different cloud providers. And on these cloud providers, the client is going to put its data. And in this work, we are looking at sharded data. So here, the client is storing different parts of data on different servers. For example, here the client may store all the patient disease information, whereas in server 2, it may store the symptoms or how treatments for those diseases. And here it may store finance and insurance related information. So it's basically sharded data stored on different cloud servers. And the client is going to execute transactions that basically read and write data to these subset of servers. Now, since these are third-party cloud vendors and the client has some sensitive application, it cannot just assume trust on these cloud servers. And we're specifically talking about the maliciousness in the servers where they're not only are curious about the data, but they're also actively manipulating the data. We are assuming that they can manipulate the data. They may deviate from executing the protocol the way they should. And the question that we ask is, how can we guarantee correct transaction execution when the data that is stored, the servers are malicious? Now, before we answer that question, I want to talk a little bit about fault tolerance versus fault detection. In most of this presentation so far, we've talked about fault tolerance. So fault tolerance is a mechanism where the system makes progress even when there are one or more faults. And this is typically achieved using replication. So let's say we have data that is replicated 3 days. Now, if one of the replicas servers either crashes or behaves maliciously, there are still enough correct replicas for the system to make progress. But the disadvantage of fault tolerance of replication is that it's very expensive. So to tolerate F crash failures, we need at least 2 F+1 replicas. To tolerate F malicious failures, we need at least 3 F+1 replicas. So the number of sites that we need to tolerate in this example, 2 sites, is we need 6 sites. And not only that it is expensive, it tolerates only a fraction of faults. So here it's saying that only one of these 3 can fail. But when we're talking about maliciousness, especially in the sense that they can manipulate and sabotage the data they have, it is difficult to say that, okay, only one of you can fail. 2 of you must always be working correctly. So an alternate to fault tolerance is fault detection. What fault detection allows is it allows the servers to fail, but what it guarantees is that it guarantees that the fault will always be detected, along with identifying which server actually caused this defect. So it is detecting the fault as well as linking and identifying the server that caused this defect. And this mechanism of fault detection has been used for a long time in building reliable distributed systems, such as peer review and CAD. And the typical idea here is that there is an auditor who is a third external entity who is going to detect, who is going to audit these servers and detect any faults. If a fault is found, an offline action, such as taking it to the court, putting a fine, such actions can be taken offline. And the main advantage here is that it allows us to tolerate more failures. So if we have n number of sites in fault tolerance, we need at least, we can tolerate at most n/3 failures. Whereas in this case, in fault detection, we can tolerate as much as n-1 faults. So what it needs is at least one server to be non-faulty. And all the remaining n-1 sites can behave maliciously, and it will still guarantee fault detection. So this is the approach that we employ in our work. Now, going back to answering the question on how can we guarantee correct transaction execution, let's start by looking at the components of each server. So in our work, every database server consists of 4 components. The first component is a transaction execution layer, which performs transactional reads and writes. Then there's a transaction commit layer, which atomically commits a transaction. That is, it ensures that either all participating sites commit a transaction or they abort a transaction. And there is the data store, which actually stores the data. And finally, there's a blockchain-like tamper-proof log that actually logs the transaction history. Now, we're going to use this tamper-proof log to provide verifiable asset guarantees. So what it means is, if a site violates any of these active properties, it can be verified by this auditor and detect any faults performed by any of the participating servers. Now, because of lack of time, I'm just going to focus on the transaction log part here. The main distinction from our work to a traditional database is that in traditional databases, the sites maintain the log locally. It logs the progress of the system just in its own server. But because we don't trust individual servers, now we need to do something else, right? So we cannot store this log just on a single server. inspired by blockchain, now we decide to replicate this log, just the transaction log, across all the sites. Please note that the data is still sharded, but the transaction log is being replicated across the servers. And so here, each block contains one or more set of transactions, and we're linking these blocks using hashes of the previous block, very similar to blockchain. One additional thing that we're doing here is we're introducing collective signatures into each block. So at a high level, what it means is individual sites produce partial signatures of this multi-signature scheme. And there is one of these sites that acts as a leader, and it accumulates all these signatures and produces the final signature. Once the signature is finalized, it is tied to a block. And if you modify the block, then the signature becomes invalid. And so an auditor can detect that, okay, your signature and your block do not match with each other. So that's the basic idea that is used here. What collective signature allows is it makes an individual block immutable once it is produced. And chaining these hashes together makes the transaction order immutable. So an adversary cannot reorder the transaction because they are hash chained. And this kind of hash transaction logs also have been used in many distributed systems, such as peer review and CATS and Microsoft Veritas. So in this work, we proposed FIDIS, which is a fully fledged database system that resides completely on untrusted infrastructure. And it uses many cryptographic techniques to provide verifiable asset guarantees. So the basic idea is we have multiple servers, each storing different shards of data. And these servers can reside either in a single cloud provider, or it can reside in multiple cloud providers. And the client is going to interact with these servers by performing transactional reads and transactional writes. This work was published in ICTCS 2020, and the conference is actually in the end of November. An integral part of FIDIS is TS commit. TS commit is a trust-free atomic commitment protocol. So if we assume trust in a trusted setting, we can use a commit protocol such as two-phase commit that guarantees atomicity. So what that means is two-phase commit guarantees that either all participants of a transaction agree to either commit the transaction or to abort the transaction. But again, as I said, it assumes trust. What if one of the servers said it will commit the transaction, but then actually does not comply to the protocol, and then it reverts its decision later point of time? This is the kind of fault we want to tolerate in FIDIS. And hence we propose TS commit, which is a commit protocol specifically meant for untrusted servers. The basic idea here is that it merges two-phase commit with collective signature, which we briefly discussed in the previous slide. And the main idea here is that once the client finishes interacting, that is reading and writing, it decides to terminate that transaction, at which point each side chooses whether it is going to commit the transaction or going to abort the transaction, along with producing a partial signature. At the end of this protocol, when the signature is finalized and recorded in the log, that signature is tied to the decision that individual sites have made. And hence, if a site decides to revert and manipulate this decision at a later point of time, it cannot do so successfully without being detected by the auditor. So that is the main idea. So we take the atomicity of two-phase commit, and we take the verifiability that collective signatures give, and we merge them in producing a new atomic commitment protocol called TS commit. So we have, there are more details about this and experimental evaluation of this protocol in our ICTCS paper. Finally, I want to finish this talk by concluding that I think it is really, really important that with all these leaks, with all these speculations about data manipulation, it's becoming really important that we should learn how to manage data in untrusted infrastructures. And I believe that we as data management researchers can help with this, and we can help the end user make their data secure. Thank you.
Okay, thank you, Sujaya. So I'd like Muhammad, Victor, Sujaya to keep your videos on. And Divi, are you still around? Have you joined us?
Yes.
Okay, why do you want to give some wise concluding words to the tutorial?
You guys have done a wonderful job. I've trained you well.
So Javan,
So
do you want?
sorry.
Javan want to jump in? Where is it?
Are there questions? I mean, what we've kind of demonstrated is that there is this notion that has been developed, the permissionless blockchain. There are interesting challenges in this very open world, in this very open, unknown number of participants, untrusted infrastructure. How do we take some of the ideas that we have developed in databases and use it in such an environment? And that's, for example, what Victor gave you, is how to do commitment in that kind of setting, how to do atomic cross-chain transactions. So how to do it. And there are lots of other interesting problems. How this will progress in the future, we don't know. I do not think Bitcoin is what's going to stay forever, but there are these ideas that I think are relevant. They are challenging us. At the same time, once we restrict it to a permissioned world for supply chains, for etc., we have a setting that is very appealing because it uses a lot of the technology that has been developed in the distributed systems world and can be beneficial in the database world. So here it's going in the other direction where we really can leverage a lot of this to do performance. So what Mohammed was talking about was sharding. That's something we as database people do a lot. And I think so there's that kind of work. What finally Sujaya ended up doing is to show you that yes, there are these nice techniques that were developed in another field, in the blockchain world, but we are facing a new world with infrastructure that is not necessarily trusted, whether this is because of cloud, whether it's even because of blockchain. I mean, there are settings where we are going to face this more and more. And now this very nice technology, the block that was developed, whether it's private or public, whether it's permissioned or permissionless, and we can use it. And then she rethinks atomic commitment. So that's another way of thinking about atomic commitment, different from the way that Victor was talking about. So I think this is kind of what our message is. And I think there's a lot of very interesting done in this field. You don't have to be sold on blockchain per se, but I think the academic intellectual challenges are quite interesting.
Yeah,
I don't know if there are questions or whatever. I mean, comments, even just random comments is good.
I have a curiosity more than a question. I just, I was wondering how this notion of shards, this commitment protocol that you guys presented, how does all this interoperate with relational system? I mean, is there any proposal on this or any assistance?
I think Sujaya can take this. Yeah.
So did you ask for relational databases?
Yeah.
So it can. So we don't really assume, in this course, we're assuming a simplistic, database, but the data store part can be any kind of queries. In our work, we assumed a simple kind of key value kind of thing, but the protocol, the trust-free commit protocol that was proposed can be employed to any kind of database. The underlying system can be a relational database as well. So mostly what it's guaranteeing is the termination of this atomic commitment. That is.
And then Muhammad can maybe also follow up from a permission point of view.
Right.
I think the techniques that is used in both sharding or even like the graph that we use for performance, can be applied to relational database as well. So these are even more like database techniques that we use in the context of blockchain. So yeah, so these techniques.
And does it scale to big graphs, like big graphs?
Or you mean for the graph, the dependency graph that we mentioned? Yeah. Or so that one, it depends on the size of the block, because the dependency graph is going to be generated for a single block. So if the block includes like thousands of transactions, then it's going to be, but usually the size of blocks is less than 1,000. So because if we want to have large blocks, then we need to wait to collect those number of transactions, and then we delay the execution. That's why we have blocks of like hundreds of transactions, and as a result, the scalability of the graph is not a concern in that sense.
Javam, the scalability of the graph is not a concern because we are not operating on the graph. It's the number of shards that is important.
All right. Okay.
Maybe speaking on this database usage of the technology. So I was thinking about this, how do you call proof of concept, which seems to be pretty costly as a function. And then when applied to a database system, as you mentioned, how would that fit? So transactions must be fast, right? So
right.
Is this
So
constraint
so
or?
I guess proof of concept becomes, or basically solving a puzzle like hashes, becomes an issue when we don't know the number of participants, like who the participants are. Whereas in our case, it's more like a permissioned blockchain where we know the participating entities.
Okay. So
it is assuming that I have a lot of data and I'm deciding on what servers I'm putting it. So the number of participating sites
I
are
see.
and hence, yeah, it is not, so we have some evaluation numbers where I think the latency is to commit a single transaction is like 1.8 times more than two-phase commit, which is not that high compared to all the advantages that we're gaining by executing this protocol.
I had also a question for, I think it was Victor, but so I grasped few things out of his talk, so I might be completely wrong. But so I was wondering, that witness component that that you presented, does it actually add a middleman kind of thing in the process?
That's a very good question, and the way. So in our archival paper, we present a centralized witness where it's a man in the middle, trusted authority, which is not a good way to do things, because in an open space, we don't have to have any trusted authority. But our final protocol, the one that I presented, depends on a permissionless blockchain, which could be actually one of the blockchains that are used for the asset transfer. So you could say, I want to transfer assets between Bitcoin and Ethereum, and I'm going to use Ethereum for coordination. So you don't need more trust than the actual underlying blockchain that we're using for the transfer.
So Fabio, let me answer that. So you're right at a conceptual level. The witness, the entity witness, is acting as a coordinator or as a middleman.
Right.
But the innovation is that middleman is not some central entity.
I see.
But it itself is a decentralized and diffused entity, like another permissionless blockchain.
Yeah,
That's kind of
got it.
So.
Yes, and I had a second question, still, Victor, I guess. And so I looked at the contracts, and they, at least in examples, they were kind of bipartite. So they have two parts. What about transactions involving multi-parts? Are they still modeled the same way? Have contracts that would cover?
Yeah, so that's a very good question. So in our situation, it won't be an issue because Alice want to transfer something to Bob, and Bob to Carol, and Carol to Alice, or Alice to Bob and Carol, and they are going to send to each other. It doesn't really matter because you could program the logic of the smart contract to transfer parts of the assets that you lock to Alice, to Bob and Carol. So it doesn't have to be two parties. And then the other thing is, in the witness network, if you read the details of our paper, we include a signed graph of the whole distributed transaction in the witness network smart contract, so that the smart contract itself knows what are the details of SC1, SC2, SC3, and so on.
Right.
So you could have as many transactions as you want. Yeah.
In fact, this is one of the main innovations that Hurley he did in his 2018 paper.
Excellent.
Compared to the original Nolan, is to take the exchange from two parties to a graph, and then we use the graph. And once you have the graph, you can actually do a lot of things. So it's a directed graph. You can have as many nodes and edges as you want.
Yeah. Mm-hmm. Okay, thank you. I think that's yeah.
Any other question, comment?
Maybe the audience.
The audience? All right. So time for a picture, Fabio. Can you do this for us? Because
yes, I can. So if yeah, everyone would show up in the camera. Let me see how you are. So if you turn on your video,
yeah, turn on your
count
video.
1, 2, 3 and smile. So let's see how it goes.
A minute.
So we have two frames. So I'll take the first one and the second one. So now for the first one, 1, 2, 3, smile. Yep. Now the second page, are all turned off camera videos. Can you turn on the videos if you want? Well, in any case, I'll take like that. Okay, done.
All right. So it's time for wrap up. So I just we had a wonderful tutorial about blockchains, and I just wanted to thank you guys. Starting with Professor Amr, but also Victor, Sajaya, Mohammed, Divi, and all the others. So I hope you guys come back to SBBD for the years to come. Hope to see you here.
Yeah, I'd love to come to Rio always.
Yeah, sure. Okay.
So I'd like also to thank Divi and Amr, Victor, Jaya, Hamad. Thanks a lot for accepting the invitation. It's always a pleasure seeing your talk. A second time I attend your tutorial. Maybe sometime I will learn about blockchain eventually.
Everyone, so be safe, everyone.
Yeah.